So an absolute or a global extreme value of a function is the highest or the lowest point on the entire graph, or on whatever the highest or lowest point on whatever section of the graph that we are interested in and looking at. So we have an absolute max in the domain of our function if the value of our function is always less than or equal to the value of one other point. We have an absolute min if the value of our function is always greater than or equal to the value at that some point. So if I was asking you on the interval from 0 to pi, what is the absolute maximum of sine x, what would you tell me? What is the absolute maximum of sine x on the closed interval from 0 to pi? It is 1. Right? And the max is always the y value. And we could say, where does it occur? It occurs at x equals pi over 2. And what about the minimum?
It would be -1.
Not on the interval from 0 to pi.
Oh, I see. Yeah, it's going to be 0.
It'll be 0. And where does that occur?
At 0 and
X equals 0 and pi.
X equals 0 and x equals pi. So we can have a absolute minimum or an absolute maximum at multiple different values, as long as they're all equal to each other, right? And as long as it is the lowest one on that particular section of the graph of our function. So what's the absolute max of our cosine function on 0 to pi?
1.
1, and we could say that it's at x equals 0. And what's the absolute min?
It's -1 at pi.
-1 at x equals pi. Easy enough?
Yeah.
Yeah, no issues with that, hopefully.
No.
All right, cool. So let's take a look at a very simple function, one that you should know everything that there could possibly be to know about it. F of x equals x squared, just your basic parabola function. And we're going to see about absolute max and absolute mins of this function on different intervals. So on the interval from -infinity to infinity, is there an absolute minimum?
0.
Should be 0, right? It should be the vertex of that parabola. That's the lowest possible point that parabola hits. Y equals 0, and it occurs at x equals 0. And what about an absolute maximum on the interval from -infinity to infinity?
What is infinity?
So a max has to be a finite value, and since it's going up forever, we would say that there is no absolute max. We would not say that it is infinity. An absolute min or an absolute max has to be a finite number. And just saying that there is none doesn't necessarily indicate that it's going towards infinity, but we'll talk about that more later. So, everybody good with that?
Yep.
Yep.
All right, what about on the interval from 0 to 2? The closed interval from 0 to 2. So we're just talking about from here to here. Is there an absolute min?
Yes. It's
0.
It's 0.
At 0.
0 at x equals 0. What about an absolute max?
It would be 4 at x is equal to 0. I said x is equal to 2.
Right, it should be 4 at x equals 2, right? We hit that point, we stop there, right? It doesn't go any higher. On the closed interval from 0 to 2, the absolute max is 4. Everybody good there?
Yep.
All right, now, what if we open up this interval here and say this is now an open interval on the 0, so half open, open on the 0, and closed on the 2? Do we have an absolute minimum?
No.
No, because we never actually get to that value of 0, right? We get very, very close to the 0. We can get down to 0.000000001, but we can always get lower than that, right? We can go to 0.0000000000000000001, or we could add, 1,000 more zeros into that, or 1,000,000 more zeros into that, or an infinite number of more zeros into that. We never actually get to 0. So there is no absolute min. What about an absolute max?
Absolute max is
2
4 at
or 4.
2.
4 at x equals 2, exactly. And if we go in and we change both of these to become open intervals, do we have an absolute min?
No.
Do we have an absolute max?
No.
No max or min. Okay. So depending on how we restrict the domain of any particular function, we may or may not have absolute maxes or absolute mins. Right? So we want to keep that sort of in mind. So I got a question that was sent in the chat about the max at 0 on the closed interval from 0 to 2. So the max value is always the y value, even though the x values go to 2, our max value is 4. So we're talking about the domain from 0 to 2. What's the highest y value we get on that? Well, the highest y value we get on that is 4. Does that make sense to everybody? So we can, even though 4 is not in the domain of 0 to 2, it's still a y value that's attained using that domain. All right, cool.
I have a question.
Yeah.
Why can't we use limits like we've learned limits? Why can't we've used them in similar scenarios? Why can't we use limits here to express getting really, really close to one point but not touching it?
You can. Sure, go for it. Say that the limit as x approaches 0 from the right is 0.
It's the minimum. Okay.
But you can't say that it's the minimum.
You can't say that it's the minimum? Okay.
No, because the minimum is not 0. It does not ever hit 0. And a minimum or a max has to be a concrete point on the graph.
Well, what if you said the minimum was the limit as you approach 0 from the right? Could you say that?
No, you cannot, because the limit as you approach 0 from the right is 0.
Okay, cool.
And that minimum is not 0 because you never hit that value. So remember that the limit is concerned about what happens as you approach that point, whereas the max and the min is what are you at that point. It's basically the exact opposite of it. The limit doesn't matter what happens when you get there, it just matters what happens as you're approaching it. But the absolute max or the absolute min, you have to get there. You have to get to that point.
Okay, cool.
Does that help? Yeah. All right. So this leads us to a fun and easy theorem, which is called the extreme value theorem. The extreme value theorem says that if a function f is continuous on a closed interval, then f must have both a maximum and a minimum value on that interval. Right? If it is continuous on a closed interval. And I'm going to make a big point about this as we move into some of our application stuff when we do some of the practice AP problems for this applications unit. And that when you will be asked to look for maxima and minima on functions. And if the function you are given has a closed interval for its domain, I'm going to remind you over and over and over again to check the endpoints of that interval to see if they are maxima or minima. And so just get ready for that. That the extreme value theorem says that if it's continuous on a closed interval, it has a max and a min. And if it's not continuous on a closed interval, it still could, but it doesn't have to. But it's guaranteed to if it's continuous on the closed interval. So we can see here, we've got an absolute max right up here. And we got an absolute min down here. Yeah. And those are somewhere within the domain. They're not at either of the endpoints. Do you guys agree?
Yeah.
The absolute max and the absolute min. Okay. And this one, the absolute min is at an endpoint, but the absolute max is not. This one, the absolute max is at an endpoint, but the absolute min is not. And this one, neither of them are on the interior, they're both at the endpoints. True? So any of that could be true. The max and the min could be on the interior, they could be at the endpoints, or it could be one of each. Good or no?
Good.
Good.
All right, what about
Good.
this bottom? What about the bottom one down here? Does this have an absolute max and an absolute min?
Yes, but are they the same value?
No.
I mean, well,
No.
let's see. You know what I mean.
So,
I think they
First-
don't have a max or a min.
okay, but isn't this defined for all the values between A and B?
Yeah, but
It's not
like
a closed
there are
interval.
points
it's not
that go
closed.
past the like.
But it's not
they have to go
continuous.
Past those.
Right, it's defined for everything on A to B, but it's not continuous for A to B. So it is not guaranteed to have an absolute max or an absolute min. And sort of like, I'm not sure, I think it was Alex maybe that was asking a minute ago that, you know, couldn't it be this limit? No, it can't be this limit. It has to be what do you get to at this point. So we get very, very close to a very, you know, whatever this y value is up here, but we don't ever get there. And so we can get very, very close to it. Suppose this value up here is 10, where this open circle is. Well, we get to 9.99999999999 as close to 10 as we want, but we don't ever get to 10. And when we hit this B, we drop down here to, we'll say 6, right? And so there's no absolute max because we keep getting bigger. We go to 9.999999999 infinitely, right? We can get as close to 10 as we want, but we never actually make it to 10. Same with 0 down here. We never actually get to 0 because when we get to x equals a, it ends up jumping back up to that other value. So this one has no max or min, and we would say that the extreme value theorem does not apply because it's not continuous on a closed interval from A to B. Whereas these ones were all continuous on a closed interval from A to B, right? There were no open circles on this. They were all continuous from A to B. So the extreme value theorem applied to all 4 of those. They both had to have an absolute max and an absolute min. Everybody good there or no?
Yeah, but I have a question about the graph at the bottom.
Okay.
If those points that were like jumps, if they were actually greater than the graph or less than the graph, could they be described as the maximum and the minimum? Like
Yeah.
if the point on the
Yes.
right was above the open circle? Okay.
Yes, they still would be the absolute max on that closed interval, but the extreme value theorem still wouldn't apply. We wouldn't have been guaranteed that we would have an absolute max and an absolute min just because it still isn't continuous, but yes, they still would be.
Okay, got it.
Does that make sense?
Yeah.
Cool. Any other questions on that? All right, so we talk about local extreme values. Yeah. And so we talked a little bit about local maxes and mins yesterday when we were looking at the graphs. So we're going to get a little bit more of a formal definition here. So a local maximum occurs as long as there is some open interval surrounding the point where that point is the highest point. And a local minimum occurs if there is some open interval surrounding that point where it is the lowest point. And we can also have these at endpoints as well. Okay. So we would say that B is a local max, right? Or not B, but the value at B is a local max because on some open interval surrounding it, it's the largest point, right? Not on this open interval, right? But some open interval. It doesn't matter as long as I can draw an open interval around it where it's the highest point, then I can say that it's a local max. Okay. we have another one up here, right? Another local max. And on our domain from A to E, this one would be an absolute max also, but it's also still a local maximum as well. And then down here, we have a local minimum. Right? And what about here at this endpoint? This should be a local min because everything to the left of it, where we have an open interval, is larger, and same here at A. Good on that, everybody. I think from yesterday's talk, you guys are probably all okay with what a local max and a local min looks like. But
Are they in like a
Yeah.
specific interval?
so when we talk about a specific interval, no, we can choose any interval around it and say that it's the local max on that interval, as long as it's an open interval. So I chose this one. It's the largest one on that. So yep, it's the local max. Had I chose this interval, still. Had I made this end over here, still true. If I made it end over here, still true. Right?
Got it.
Does that help?
Yeah.
Yeah, it doesn't have to be one specific one. And so we couldn't, if we tried to do this, right, say that open interval there to try to find a local max or a local min on that, well, we couldn't because it's an open interval, right? And so as we go towards whatever this almost endpoint is, we don't actually get to that y value on either side. And so since it's an open interval, we can't just arbitrarily choose any point as a local max or min. It has to be one that's actually the highest on an open interval surrounding it. Everybody good or no?
So is C also a local min?
Yeah, C is a local min, yeah. I didn't write local in front of it, but yeah, C is a local min. And on this interval, it would look like that, I should have written, I just didn't write local in those. These are all local mins and maxes. This one at D happens to be the absolute max, and the one at A happens to be the absolute min on the closed interval from A to E. And we would be guaranteed by the extreme value theorem, if we knew this was a closed interval from A to E, that since this is continuous, there has to be an absolute. And so we can put that in. That's the absolute and the local, and this is the absolute and the local max at D. So even a little more specific now. Everybody good there?
Yeah.
Cool. So a function can have a local minimum or a local maximum at a place that is on the interior of its domain. So we're not talking endpoints here, but we can have a local minimum or a local maximum at an interior point of its domain if the derivative equals 0, or if the derivative is undefined at that point. Okay. And this is a very critical piece of information, pardon the awful pun here, but a place where the derivative equals 0 or a place where the derivative does not exist is called a critical point or a critical value. Okay. And so when I ask you to find minima and maxima, your job will always be, first off, to find critical values or critical points, places where the derivative is 0 or where the derivative doesn't exist. And so we've already talked about the derivative equaling 0, right, where we have a horizontal tangent line. That's where we have a local min or a max sometimes. But also at a place where the derivative is undefined, because a corner or a cusp could be a local min or a local max as well. Everybody see that?
Yeah.
Yeah.
All right, cool. So when I ask you to find local maxes and mins, or even absolute maxes and mins, you're going to have to check all of the critical values and see which one is a max and which one is a min, or they may not be either. It just sort of depends on the problem. Okay. This little note down here that a place where f prime is 0 or f prime equals 0 is called a stationary point. That's not super important. Just know that places where the derivative is 0 or where the derivative is undefined are called critical points. Good?
It does not exist. Okay, yeah, never mind.
Okay.
And those critical points are where local maximums and local minimums are.
They are, yeah, they are the only places where local maximums or minimums can occur on the interior of the domain of a function. Is a place
Oh,
where
so
the
it's not
derivative is.
guaranteed.
It's not guaranteed that it will be. We'll see some cases today where it's not. But it's the only place where they could. And generally they do, but not always. So don't assume that it will be if the derivative is 0 or doesn't exist. And that's one of the things that people sort of get caught up in, is they say, oh, the derivative is 0, must be a local min or a local max. Well, that's not true. But it's likely true, but it's not guaranteed to be true. But it is guaranteed that you will not have a local max or a local min on the interior of the domain of your function unless it's a critical point. So one way it's true, the other way it's not necessarily true. Does that make sense?
Yeah.
So critical points are, if they don't exist, then
If
it's
the
always a
derivative-
critical point.
If the derivative equals 0 or the derivative does not exist. So if f prime is 0 or f prime doesn't exist at some x value, that's a critical point or a critical value. Everybody good or no?
Yeah.
All right. So what we want to do then is we want to see if we can find the absolute maximum and the absolute minimum values of f of x equals 2/3 on the interval from -2 to 3. So this is not just asking for local minimum and maximum, it's asking for absolute. And we are also given a closed interval. So what does that tell us about the absolute max and the absolute min? Do they both have to occur?
Yes.
Yes, because of the extreme value theorem, this is a closed interval. This function is continuous from -2 to 3. We are guaranteed to have an absolute max and an absolute min. Now, there are multiple possibilities as to where those could occur. They could occur at the endpoints, right? Just like when we looked at all these pictures, right? They could occur at the endpoints, but they could also occur at an interior point. True?
Yeah.
So, based on this information up here, that a local max or a local min could occur at an interior point if the derivative is 0 or the derivative is undefined, we need to check places where the derivative is 0 and where the derivative is undefined, and we need to check also the endpoints. So we need to check critical points and endpoints. Everybody good with what we're doing there to try to find the absolute max and absolute min?
Would we also have to specify that it's continuous?
No, you don't need to specify that it's continuous for this. We're not applying any theorems, so we're not like trying to show that there are, not trying to show that this theorem applies, that the extreme value theorem applies. We're just trying to find what those values are. And like somebody, I think it was Alex asking earlier, maybe it was someone else, that if these points were up higher, right, if it wasn't continuous, but this point was up higher, then that still would be the absolute max of the function on the closed interval from A to B. So.
Okay, thank you.
Yep.
Did we prove this yesterday by graphing the derivative graph?
Did we prove it?
Like when we like graph the derivative of the function, when like the derivative is equal to 0, that's when like there was the like turns in like the curve.
Yeah, I mean, we didn't prove it, but that's, I mean, we saw that that's the case, that when we have that local max or a min, that's when the derivative was 0. Yeah. And so we added in the little caveat, I think I drew pictures down here, that we could have a local max or a min at a cusp or a corner also, which would be where the derivative is undefined, right? We could still have a local max or a min at something like those. And so it's not just where the derivative is 0, but it's also where the derivative doesn't exist, that it's possible to have that max and min. Is that good or no? Everybody good? Yeah, no, maybe?
Yeah.
All right, so let's do this. Let's see if we can first off find the critical points. So if we want to find the critical points of x to the 2/3, what do we need to do to it?
Find its derivative.
Find its derivative. And what's f prime of x?
2/3 x to the negative 1/3.
2/3 x to the negative 1/3, or 2 over 3 x to the 1/3. If I drop that negative exponent down. Good or no?
Yeah.
All right. When does that derivative equal 0?
Never.
Never, right? The answer is never. It never equals 0, because in order for a fraction to equal 0, the numerator would have to be 0, and 2 is never 0. So then we'll also look, when does 2 over 3x to the 1/3 undefined? Well, it would be undefined if what part of the fraction equaled 0?
Denominator.
If the denominator was 0. So this is undefined if 3x to the 1/3 equals 0, which if we solve that for x gives us x equals what?
0.
0. All right.
0.
So we have 3 different options for where we might have an absolute maximum or an absolute minimum. What are those 3 options?
-2, 0, and 3.
-2, 0, and 3. Exactly. So let's figure out what is f of -2, what is f of 0, and what is f of 3. Our original function was just x to the 2/3, right? So what's 0 to
Yeah.
the 2/3? That one, 0 to the 2/3 should be easy. That's 0, right?
Yeah.
What about 3 to the 2/3 power? I mean,
Cube root of 9.
yeah, well, sure, we can write it like that. Cube root of 9. And what about -2 to the 2/3 power? That's the cube root of
4.
4, right? So which one of those is the largest value?
Cube root of 9.
Cube root of 9. So our absolute max is cube root of 9 at x equals 3, which is an endpoint. And what's our absolute min?
0.
0. And that's at x equals 0. And that's at an interior point, right? So we can
Yeah.
see that it could have occurred at an endpoint or it could occur at an interior point. Good?
Are endpoints not critical points? Because I thought you said before that it can only happen at critical points.
Okay, so I did not say only at critical points. I said on the interior
Oh, it's okay. For
of the domain of a
interior.
function. Oh, sorry, this is not the right slide, but yeah, here it is. Still at an interior point of its domain, we can have a local max or a min. And so when we talk about closed intervals, it's you could have the local max or the local min on the interior point, which could also be an absolute max or an absolute min, or it could be at the endpoints. Does that
So
make sense?
closed interval, we also have to make sure we check endpoints.
If it asks for absolute max and min, yep.
Okay, cool.
Any questions on that one? Are we good with that now?
All good.
All right, let's do another one. So let's find all of the extreme values for 1 over root 9 minus x squared. I don't know what happened to my fraction bar there. It looks like it's disappeared. That's not any better. There we go. That's better. So we want to find all the extreme values of this. How are we going to do that?
Do what we did before.
Do we have an
All right.
interval?
We don't have a given interval to this, do we? So that's an issue. So we need to figure out the interval should be negative infinity to infinity if that was the domain of this function. Is that the domain of this function?
No.
No, it's not.
No.
So we should probably figure out what the domain of our function is first before we even bother to take a derivative. So how do we figure out the domain of 1 over root 9 minus x squared?
Set the denominator equal to 0, and then that can't be in our domain.
Right, that can't be, but what else can't be? not just if that equals 0, but also if the 9 minus x squared is
Be negative.
Negative.
right, if the 9 minus x squared is negative. So our domain is only values that make 9 minus x squared what? Greater than 0, right? Positive. Yep. Or effectively, if x squared is less than 9. And how do we solve that? If x squared is less than 9, that would mean that x is less than 3 or greater than negative 3. So what do we have here? We have an open interval, right? For our domain.
Yeah.
So that means the
Yeah.
extreme value theorem does not apply. It means that we're not guaranteed to have an absolute max and an absolute min. We still could, but we're not guaranteed to have them. And do we need to check our endpoints?
No.
No, because there aren't any, right? There's no endpoints to check. So how would we check something that we can't actually, that doesn't actually exist? So now the only possibilities for absolute maxes or absolute mins will be at the critical values. So let's find f prime of x. So this is like having 9 minus x squared to the negative 1/2, right?
Yeah.
So how do we take the derivative of u to the negative 1/2 using the chain rule, right? Should become negative 1/2
Negative 1/2 times 9 minus x squared to the negative 3/2 times 2x, or negative 2x.
negative 2x. That's the chain rule, right? U to the negative 1/2 is negative 1/2 u to the negative 3/2 times the derivative of u times the derivative of 9 minus x squared, so negative 2x. And if we simplify that down, what do we get? The negatives will cancel, the 2's will cancel. We got an x in the numerator, and in the denominator, we've got 9 minus x squared to the 3/2. So now, let's think about any values that make this equal to 0. Are there any values that make this equal to 0?
0.
If x equals 0. And what about any values to make this undefined?
If denominator is 0.
Right, if our denominator is 0, that would make it undefined. What makes our denominator 0? 3 does, also negative 3. But are 3 and negative 3 in the domain of our original function?
No.
No.
And so we can't have a critical value at a point that is not in the domain of our original function. And if we go back here, a function has a local minimum or maximum at an interior point C of its domain. Well, those points that we just found, 3 and negative 3 for this denominator, are not in our domain. So we'll say this is undefined never on the open interval from negative 3 to 3. So our only critical value is x equals 0, and x equals 0, well, should either be a absolute max or an absolute min, most likely. First, let's figure out what is f of 0.
1/3.
Should be 1/3, right? And how are we going to determine if it's a max or if it's a min? There's a couple different ways we should be able to do this.
Plug in some other points.
Oh, we could just plug in another point, right? See if we get something bigger or less than 1/3. So plug in something like 1, just to test. If we plug in, well, 1's not so great. Suppose we plug in, we'll just plug in 1, that's fine. If we plug in 1, what do we end up with? 1 over the square root of 8. Okay.
Yeah.
And which of those is larger, 1/3 or 1 over the square root of 8?
1 over the square root of 8.
Right, that's greater than 1/3. So can 1/3 be an absolute maximum?
No.
No.
No. So it should be an absolute min of 1/3. at x equals 0. That's one way we can check. And we're going to see another way to check maybe later today, depending on how much we get through. Good or no?
Good.
All right. So just real quickly, I know we said that if we had a critical value where it was 0 or where it was undefined, that it might be a local max or a local min. I just want to give an example of when that might not be the case. So what about y equals x cubed? What's the derivative of that?
3x squared.
3x squared. When does that equal 0? When x is
X is
0.
0.
0.
What does y equals x cubed look like? Looks like this, right? Is there a local minimum or a local maximum at x equals 0?
No.
No. So just because we had a critical value doesn't necessarily mean that it's a local min or a local max. Okay. Good?
Yeah.
All right, so you have to go and you have to do some work to check. All right, and we'll see more about what that work would be, like I said, later today. What about this one? What's y prime? 1/3 x to the negative 2/3?
Yeah.
Never equals 0, right? But it's undefined if x is
Negative
0.
or no 0.
Yeah, just if x is 0, right? Because I can cube root any number, positive or negative. So this is just undefined if x equals 0. Well, what's the cube root of x look like?
Cusp.
No cusp on it.
Oh, it's the x to the cube reflected over the y equals x.
Exactly. It's just the inverse function of x cubed, right? It's just x to the 3rd power reflected over y equals x. And it's the same thing. There's not a local max or a local min at x equals 0. So, like I said, you just want to make sure that you check and make sure that it is that local max or min. Everybody good so far?
Yep.
All right. Let's find the extreme values of 5 minus 2x squared if x is less than or equal to 1, or x plus 2 if x is greater than 1. So piecewise defined function. Any thoughts on how we'll start that?
Find a domain.
All right, find the domain. So first off, if x is less than or equal to 1, tells us that we should be able to plug in everything less than or equal to 1 to that, hopefully. Are there any values we can't plug into 5 minus 2x squared?
No.
No. All right, are there any values we can't plug into x plus 2?
No.
No. So what's our domain?
Negative infinity.
Domain is negative infinity to infinity. Are we guaranteed to have an absolute max and an absolute min?
No.
No, but there still could be. So let's take a look. 5 minus 2x squared if x is less than or equal to 1, and x plus 2 if x is greater than 1. So let's just take the derivatives of both of those and see when each one is 0 and see when each one is undefined. So for x less than or equal to 1, what is f prime of x equal to?
Negative 4x.
Which negative 4x equals 0 at x equals 0. And is negative 4x ever undefined?
Nope.
Nope. All right. So what about for x greater than 1? What is f prime of x equal?
1.
Should be 1. Is that ever equal to 0 or is that ever undefined?
Nope.
No.
Nope.
Okay. All right. So now And okay, I made a small thing here I shouldn't have done. Should have said for x less than 1. We're not going to look at it at that endpoint of 1. But so for x less than 1, the derivative is negative 4x. So do we have any critical values?
X equals 0.
Just x equals 0, right? And we want to make sure, right, that this is never undefined. We want to make sure that that x equals 0 value is included in x less than 1, right? Because if I'd come up with x equals 2, well, 2 is not less than 1, so that wouldn't be in the domain of this piece of my derivative. Everybody agree with that?
Yeah.
Yeah.
All right. What about f prime of 1? In order for the derivative at this point 1 to exist, what would have to be true? The derivative from the left would have to be equal to the derivative from the right. So the derivative from the right is 1, right? Well, it says negative 4x evaluated at x equals 1 equal 1.
No.
No, right? Negative 4 does not equal 1. So do I have a derivative that exists at x equals 1?
No.
No. So f prime is undefined at x equals 1. So how many critical values for this function do I actually have?
2.
2.
Two.
X equals 0 and x equals 1 are my critical values. Everybody see that and agree with that?
Yeah.
Can you explain why x equals 1 is a value?
Yeah, so since we have a discontinuity or a potential discontinuity in our graph here at 1, because we've split from one function to another, we need to check the derivative specifically at 1. And so for the derivative at that split to exist, the derivative of the left-hand piece has to equal the derivative of the right-hand piece at x equals 1. So the derivative of the left-hand piece was negative 4x. And at 1, negative 4x is negative 4. And the derivative of the right piece was just 1, so that's just 1. And so we end up with negative 4 equals 1, which is not true. And so since those aren't the same, that means that the derivative is undefined at 1. But if they were the same, then we could say that the derivative equaled, if they both equaled 1, then we could say the derivative was 1 there. Does that make sense?
Yeah, thanks.
All right, so we've got two places where we might have local minima or maxima, or also absolute maxima or minima. So now, let's first off see what those values are. What's f of 0?
Five.
5.
Should be 5. What's f of 1?
3.
Should be 3. Yeah, both of them from the 5 minus 2x squared. So clearly 3 at f of 1, or sorry, 3 at x equals 1 is not an absolute max, but f of 0 equaling 5 could be an absolute max. How are we going to determine if it's an absolute max or just maybe a local max?
Plug in -1.
Okay, so if we plug in -1, what are you going to get?
3.
3.
3, right? So we know that it's to the left of 0, it's getting smaller than this. And to the, what about to the right of 0? What happens? Between 0 and 1, it's also getting smaller, right? But what about once it gets greater than 1?
It's also decreasing.
As x gets greater than 1?
It's increasing.
Oh, crap.
Should be increasing, right? Because when x is greater than 1, it becomes x plus 2. So like if x is 1,000, right? If x is 1,000, clearly 1,002 is more than 5. So this cannot be an absolute max, just based on the nature of our function. We could determine that by looking, let's say, at the limit as x approaches infinity of f of x. What is that limit?
Infinity.
It's infinity. So I know that I'm going up much larger than 5 eventually. And what about the limit as x approaches negative infinity of f of x?
Negative infinity.
should be negative infinity. So I'm not going to have an absolute max, and I'm not going to have an absolute min, because as my function gets very large x values or very small x values, the y values get very large or very small. So these are just local values. So we have a local max of 5 at x equals 0. And then we were decreasing down to this value of 3, but then as soon as we hit 1, we started increasing again. So this becomes a local min of 3 at x equals 1. Everybody good with that or no?
So is that how you check if it's absolute or local? You do limits at infinity and limits at negative infinity?
That's one way that we check, yeah. And when we don't have a closed interval, yes, that's a good way to check if it's an absolute rather than just a local.
Okay.
Yep.
So why are we only using the top function of the piecewise? Because there's like 2 functions within this function, so why wouldn't we be using the bottom one at all?
Well, we did a little bit. We tried to take the derivative of it, right? And said that its derivative was always 1. And therefore, it was never 0 and never undefined. So there were no critical values from the x plus 2 piece.
Oh, I see.
Right, so we did that right here. And then we did also use it here when we looked at the limit as x approached infinity, right? As x approached infinity, that's infinity plus 2 or infinity. So we knew that it was increasing forever. But we didn't use any values from that because the derivative was never, the derivative of that piece didn't have any critical values on it.
Okay.
Everybody good?
So if the domain wasn't negative infinity, infinity, if it was a different open interval, would you test it by taking the limit of just the domain, like the minimum of the domain and the maximum of the domain?
Yeah, you could do that. That would work, yeah. And you'd want to see if it gets to be a higher or lower value than 5 or 3.
Okay.
Yep. Any other questions there? All right, let's do this one. This will be a fun one, yeah? Any thoughts on this one?
Find the domain.
Yeah, we still need to find the domain first.
All right, finding the domain. Yeah, that's always a good thing to do. So how are we going to do that?
Denominator can equal 0.
Okay. So we'll start with 1 plus x squared cannot equal 0. Well, does that ever happen?
No.
X squared cannot equal -1. Okay, that's fine, right? X squared definitely can't equal -1. All right, so that's good. What else? The thing inside of there can't be equal to what?
0.
Right, the whole thing, x over 1 plus x squared cannot equal 0 also. When does that happen?
When the numerator is
X is
0.
0.
Right, so that'd be when x is 0. So we do have a restriction in our domain. Our restriction is that x cannot be 0.
Yep.
Yeah. All right, so we got a domain of negative infinity to 0, 0 to infinity. Are we guaranteed to have absolute maxes or absolute mins?
No.
No, but we could find potentially local maxes or local mins, right?
Yeah.
And we could also still have an absolute max or an absolute min. We're just not guaranteed to have one. All right. So how are we going to figure out when the derivative of this equals 0? We got an absolute value in there, which is a little bit of an issue, yeah?
Yep.
All right. So if x is greater than 0, is x over 1 plus x squared greater than 0?
Yes.
Yeah, right, because the numerator is going to be positive if x is positive. And no matter what x value we have, the denominator is always going to be positive, right? A positive number plus another positive number will always be positive.
Yeah.
All right, so then this would just become natural log of x over 1 plus x squared, or x greater than 0, right? Because if you're taking the absolute value of something that's positive, it just comes out to be the same thing that inside of there. I'm sorry, if you're taking the absolute value of something that's positive, it just comes out to be that same positive thing. So how do I take the derivative of natural log of x over 1 plus x squared?
Chain rule.
Reciprocal.
Yeah, so no, not the reciprocal rule, just the chain rule, right? Natural log of u, so 1 over u, times the derivative of u, so times the derivative of x over 1 plus x squared, which will be 1 plus x squared times 1 minus x times 2x all over 1 plus x squared squared. Good or no?
Yeah.
All right.
Good.
All right, so we're going to simplify what's inside of the parentheses here first. That's a 1 plus x squared minus a 2x squared, so that becomes what?
Negative x squared.
Yeah, 1 minus x squared, and then over 1 plus x squared squared. And then we've also still got this. Well, if I just take the reciprocal of this and multiply, I should end up with a 1 plus x squared up here and an x down here. Everybody agree with that?
Yeah.
Okay. So that gives us 1 minus x squared over 1 plus x squared times x. And when is this undefined?
X equals 0.
X equals 0. Is that in the domain?
Nope.
No.
No. So not in domain, can't be a possible absolute max or min. What about this? When does this equal 0?
At x equals 1.
X equals 1 and x equals -1. Is x equals -1 in the domain of the piece that I just took the derivative of?
No.
No.
No. So we'll ignore that for now, although we're going to have that pop back up in a bit. We've got a critical value of x equals 1. Everybody agree that we can ignore the 0 and the -1 and only get x equals 1?
Yeah.
All right. So then, what about when x is less than 0? Then the natural log of the absolute value of x over 1 plus x squared becomes what? The natural log of the opposite of x over 1 plus x squared? True, because x over 1 plus x squared is negative?
Yeah.
Okay, good. So now we just want to find the derivative of natural log of negative x over 1 plus x squared. Well, it's going to look very similar, right? 1 over negative x over 1 plus x squared times the derivative of this. Well, that's just going to be negative. And then same thing that we did before, right? 1 plus x squared times 1 minus x times x times 2x all over 1 plus x squared squared. Basically the same derivative, except the first piece of it has a negative sign and the second piece of it has a negative sign. So when I multiply those two negatives together, I'm going to get positive.
Yep.
Yeah.
And I'm going to end up with the exact same derivative that I had for the other one. 1 minus x squared times 1 plus x squared over x times 1 plus x squared squared. And once again, this equals 0 at x equals positive or -1, and it's undefined when x equals 0. And this time, that's still not in our domain, but we'll just choose the -1 value. Good or no?
Yeah.
Okay. So we have two critical values. Everybody good on why we just chose -1 for that one?
Yeah.
So those are our two critical values. Let's find f of 1 and let's find f of -1. F of 1 is the natural log of what? 1 over
Half.
2, so natural log of a half. And f of -1 is what? The natural log of?
-1/2.
No, because remember it's inside of an absolute value, so natural log of a half. Right? So we've got the same value. So if one of them is an absolute max or an absolute min, then the other one is as well. True? So let's just figure out what's going on then with our function outside of these values. So let's look at the limit as x approaches -infinity of f of x. We'll just write of the natural log of the absolute value of x over 1 plus x squared. What happens to that?
Infinity.
So it's not infinity. What we need to do is we need to make a substitution. So let's substitute out this x over 1 plus x squared, or even the absolute value of x over 1 plus x squared. So as x goes to infinity, let's just do this. As x goes to -infinity, what does u approach? And we'll do it with the absolute value. What does u approach?
Zero.
It should be 0, right? That's just a
Oh.
horizontal asymptote of a rational function. So u is approaching 0. And if this is inside an absolute value, then it must be approaching 0 from which side?
The left?
Left.
No. If this is an inside of an absolute value, I'm approaching 0 with using only positive numbers. So I'll be approaching 0 from the right-hand side. Good or no? Okay. So this becomes the natural log of u, and a limit as u approaches 0 from the right, which is what?
-infinity.
-infinity. So as we go to the left, away from -1, going to the left, we're going down to -infinity. So this value here is larger than everything that is to the left of it. What about if we look at the limit as x approaches positive infinity of the natural log of the absolute value of x over 1 plus x squared? What's going to happen? We're going to do the same substitution, right? And what are we going to end up with? If I do the same substitution as I go towards infinity, this is still going to be approaching 0 from the right-hand side. And so it's still going to be -infinity.
Yeah.
Okay. So that takes care of what happens as x gets very, very large and very, very large and negative, right? But we also have something else happening with this, which is that we have a discontinuity at 0. So we got to make sure we know what's happening at 0 as well. So let's see if we can figure out what's the limit as x approaches 0 from the left of the absolute value of x over 1 plus x squared. Well, what should that be?
Zero.
0, yeah.
Can I take, I'm sorry, from a natural log? That will probably affect your answer.
Does it not exist?
So right, this is again, it's non-existent, right? But the question is it infinity or is it -infinity? So let's do this same substitution. Let's let u equal the absolute value of x over 1 plus x squared. And as x goes towards 0, well, this is going to be approaching 0 from the
It's gonna be approaching 0 from the right.
Because it's inside the absolute value, right? And so what is that going to become? It's going to become the limit as u approaches 0 from the right, again, of the natural log of u, which is negative infinity. So it's going to be falling again. And what about if I do the limit as x approaches 0 from the right? Same thing's going to happen, right? It's still going to be 0 inside the absolute value, and it's still going to be approaching 0 from the right. We're going to get negative infinity again. And so we should be able to tell then that to the left of -1, it's falling, and to the right of -1, it's falling, both to negative infinity. And both to the left of 1 and to the right of 1, it's falling to negative infinity as well. And so what does that tell us? It tells us that we have an absolute max of the natural log of a half, and it occurs at x equals positive and negative 1. Good or no?
Good.
Well, that's okay. Let's take a look real quick at the graph of it, just because you probably aren't super familiar with what this graph looks like. So natural log of the absolute value of x over 1 plus x squared. And that's what it looks like. So on Desmos, we can see clearly that here, there's -1, there's our max, and that's the natural log of a half right there. And that's also the natural log of a half right there. And it's falling slowly to negative infinity as we go to the left and to the right, and as we go towards 0 from the left and from the right. Everybody good with that?
Is this going to be on our quiz this week?
This particular problem won't be on your quiz this week.
But like stuff like this?
Probably nothing quite this difficult, but stuff with the absolute max and the absolute min stuff, yeah.
Okay. And have you picked like a finite date, or are you not going to tell us just any date coming up?
Let's go with not tomorrow.
Not tomorrow, sweet.
Yeah, if that's helpful at least. All right, any questions on that last problem or anything we've done today?
Can you go back like 2 pages?
Sure.
Why is it for the stuff on the left, you said it was like approaching it from the right side?
U is approaching 0 from the right. If U is the absolute value of x over 1 plus x squared, then as x goes towards infinity, just x over 1 plus x squared goes towards 0. And since it's inside of an absolute value, it's got to be approaching 0 from the right-hand side because it's always going to be positive numbers.
Oh, got it.
Cool. Any other questions?